If we let nature do its thing, mangroves could survive sea level rise by either building soil or migrating inland. Well, they cannot go inland because we're there. So they can only build soil. So at some point, they're sandwiched. It's the famous mangrove squeeze, and they're squeezed out of the earth. And at some point, we're just gonna have to build a wall to protect ourselves from the sea, which is not super efficient and definitely costly. You save a lot of money if you just keep the mangroves where they are.
Hi, I'm Stephanie Tomampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring stories of resilience, hope, and scientific insight into climate change. Today, we're discussing a topic we've never covered on Down to Earth, wetlands. So grab your waders, because we're going in. This episode of Down to Earth is brought to you by the Remote Sensing Environment Analysis and Climate Technologies, or REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society. The REACT Technical Committee is a collaborative and supportive venue for all scientists and engineers looking to exchange ideas and share knowledge that advances our efforts to tackle climate change. To learn more and be part of this incredible cutting-edge community, visit grss-ieee.org and select the REACT Technical Committee.
My background is physics, and I started doing remote sensing using instruments that are radars. And with radars, we look at the structure of the land surface, the water surface. And wetlands are particularly dynamic. Not only is the water level changing with time, whether it's through season or along the coast with tides, but they're extremely dynamic, and they offer a challenge to remote sensing measurements. Not only to remote sensing measurements, but wetlands are regions that are really difficult to access and do field work.
This is Dr. Marc Simard. He's a senior scientist at the NASA Jet Propulsion Lab in California, where he specializes in remote sensing of coastal zones, coastal regions, wetlands, and their ecosystems.
So remote sensing offers really the opportunity to look at wetlands at the very large scales that we need to study them. So when you go in the field, you take a sample, and you may have a quad like 50 centimeter by 50 centimeter. And with remote sensing, 50 centimeter is not even a pixel. So we have to make the link between those different scales. And with remote sensing, we just get a broader perspective, although not as accurate as the field. In the broader sense, it's a really fantastic tool.
Marc is the principal investigator of the Delta X project, a 5-year NASA Earth Venture suborbital mission that examines how land is lost and gained in river deltas. This research is incredibly important because deltas are sinking. You heard me right. They are not able to grow fast enough to outpace the rapid rise in sea levels, so they're disappearing. Delta X hopes to shed light on which parts of the Mississippi River Delta, the delta chosen for this study, will survive and continue to grow, and which parts will be lost. This data will then help us better understand the change in deltas all around the world. Now, before we jump into Marc's research, I want to give a quick background on wetlands, because we've never talked about them on the podcast before. So a wetland is an area of land that is either covered with water or saturated with water for at least part of the year. They are transitional environments that have neither completely dry land nor completely submerged land. The water in a wetland can come from many different sources. For example, groundwater might seep up from an aquifer or spring. A river or lake might cover a wetland area every time the water is high, or in the case of coastal wetlands, they experience tidal changes to water levels. There are saltwater wetlands and freshwater wetlands, and the name used for a wetland, like swamp, marsh, or bog, is determined by the biochemical processes and geomorphology of the wetland. Wetlands exist on every continent in the world, with the exception of Antarctica, and they are covered with a diverse selection of vegetation. One wetland ecosystem that has been getting a lot of attention from climate change researchers is mangroves. These ecosystems have been dubbed by the UN as a super solution carbon sink since they are able to store 4 times more CO2 than rainforests. They also provide important storm and sea level rise protection along the coastal regions where they grow. Now that you have a basic understanding of wetlands, let's learn more about how Marc studies them and what he's learned so far from the Delta X project. So, Marc, you have been studying wetlands for a long time, and in particular, you have a lot of expertise in mangroves. I come from a small island in the Philippines surrounded by mangroves, so I have a special affinity for this ecosystem. Can you tell us more about what makes mangroves so special?
Mangrove forests are known for their ecosystem services. They provide habitat and they are significant players in the carbon cycle. But the main service that mangroves offer is protection of the coastlines. And when you talk about protecting the coastline, you can be protecting the mangrove forest itself, the ecosystem and its services, but you're also protecting what's behind the mangrove, which is people. So when you have a storm surge, you have daily erosion from waves. Mangroves keep the coastline where it is. And as sea level rises, they contribute to elevating the soil with the sea level rise.
I've also read that mangroves can absorb more carbon than terrestrial trees. Is this correct?
Yes, that's correct. So they're super efficient, several times even the tropical forest. And in addition to that, because they, let's say, inject the carbon into the soils, that's where you find most of the carbon stocks in the mangrove forest. It goes into the salt water, and decomposition rates are much, much slower. So the carbon stays there for thousands of years. So you have around 1,000 tons of carbon per hectare. So the rates of the carbon stocks in the soils of mangroves is huge.
That's a big deal. And it makes me wonder why, when we talk about climate change, we don't see people talking about wetlands that much. Why do you think this is the case?
I'm not sure why. So they capture a lot more carbon than any other types of forests, and I think their socioeconomic services might actually be greater than any other types of forest. So more emphasis should be put on wetlands and their contribution and the role they have on the carbon cycle and climate change. At NASA, we do include wetlands in our research, and I think there should be definitely more discussions about how to preserve and promote wetlands for the impact and role they have.
Well, let's talk more about that. How do we study mangroves at NASA? And what are we looking to understand?
At NASA, we observe the Earth as a planet, as a system. We're trying to understand how the Earth functions. We try to understand how the ecosystems interact with the hydrology. We try to understand or quantify even their vulnerability to climate change. And this is what I'm trying to observe. So, vulnerability of mangrove forests. You know, if you lose a mangrove forest, you also lose its services. So, it's very important to understand how vulnerable they are to not only climate change, but to human activity. You know, we tend to encroach into coastal areas. We like to have beaches and we like to eat. We build the shrimp farms and we build houses with the wood. So there's a lot of things we can do with those mangrove forests. But doing that, we remove their ecosystem services as well. So it's important to monitor them at the global scale. It's nearly 40% of the world's population live within about 100 kilometers from the coast in the tropics. That's where you find a mangrove forest from 30 degrees south, 30 degrees north approximately. So in the tropics, that is where those mangrove forests are important to monitor. And their vulnerability depends on several factors. Of course, it's the vicinity to human activity, urban areas, and agriculture. But there's also something with their structure. And their structure includes the size of those mangroves. For example, the larger they are, the denser they offer more protection to storm surges, for example. They dampen the waves and the tide. And now with radar remote sensing, we're able to measure all that. We're able to measure mangrove canopy height from space everywhere on Earth. So we don't need to send armies of people making measurements. We actually can measure it from space thanks to new radar technologies. So this is what I'm observing mainly. And of course, height of the trees is also related to the amount of carbon that's stored in the wood of the trees. So what we call above ground biomass. So height, the taller a tree, the more biomass it has. So we're able to account for the carbon that's stored in those trees rather than in the atmosphere. So there's a lot of processes here happening, and structure is one of the determining factor of those processes.
So, mangroves are vulnerable to human activity and sea level rise. But I also read that salinity of the water can play a role in mangrove degradation. How vulnerable are they to high salinity levels? After all, don't they live in brackish waters?
Yes, so mangroves are found along the coast in the intertidal region. Intertidal means the high tide versus low tide. So the mangrove forests live in that region. So mangrove forests are resistant to salinity. It's not that they like salt, they just can't survive salt. They're salt tolerant. You can actually grow a mangrove tree in a pot behind your house, but you have to keep all the other species, all the grass out of your pot. You have to make sure it doesn't compete too much with other species, but they can survive in those intertidal regions. So typically salinity is a stressor on mangrove structure. So tall forests will be found in less saline area. The saltier the soils and the water, the smaller the trees will be. If you just look at the Everglades, for example, you have 4 species of mangroves, including buttonwood. So you have very tall mangroves along the Shark River, which has this freshwater input. So the salinity is lower. So you have tall forests. And the same species in Taylor Slough, which doesn't have so much fresh water coming in, it's more salty. The same species are small. So the salinity will control mangrove structure.
So, if I understand this correctly, the height of the mangroves helps you determine both the salinity of the water and the amount of carbon absorption happening in the mangroves. Is that correct?
Yes, basically, the mangroves are by their structure. They're telling you something about their environment. They're telling you how saline it is. They're telling you how much nutrient they have. The size of the mangroves tell you about the local environment they live in.
Hmm. Okay, let's talk about the remote sensing being used to study the mangroves. What satellites are you using?
Okay, currently I've been using satellites that are defunct now. The data still exists, but they also provide a baseline of the mangrove structure in the past. One of the big data sets that we've been using, a globally available data set, is the Shuttle Radar Topography Mission. It was an instrument installed on the space shuttle that flew in February of 2000, provided the first global picture of mangrove canopy structure, vertical structure. And nowadays, I use 2 new radar satellites. One of them is called Tandem X, which is from the German Space Agency, and it provides a digital elevation model of the Earth. And that is that elevation model that we use to map mangrove canopy height. And I also use a Japanese satellite called ALOS Pulsar. There was a one in 2007 through 2011, and there's a new one called ALOS 2, Pulsar 2, which is a radar that doesn't measure height of canopies, but it measures wetland loss. So whether you're in marshes or mangrove forests, you can look at the coastline and the migration of the coastline toward the ocean or inland. And I also use Sentinel-2 and Landsat, of course, which work really well. Oh, yeah, there's another one that gets really good measurements of canopy structure, It's called Jedi, just like in reference to Star Wars.
Yeah.
It's a laser altimeter that was flying in the last few years over the International Space Station. It will be coming back online in a couple of years, but right now it's stored in a closet up there. But it's been measuring canopy height globally everywhere, not only mangrove forest, but also inland forest, tropics and boreal and temperate forests.
I've seen some mangrove forests, like how you see it from up above. Sometimes it's mixed with the terrestrial plants. How do you separate those?
Yes, so that's a very good question. So sometimes you have a mangrove forest, and behind it, maybe there's a mud flat or there's a desert sometimes. They're really easy to map. But sometimes, as you said, there's a forest behind it, which is as green as the mangrove forest. So how do you distinguish those two types of forests? And yes, that is a very difficult thing to do. One of the ideas that we have implemented is the use of the DEM, which is the digital elevation model, so the elevation of the earth. Mangrove forests grow at sea level within the intertidal region, and other types of forests are above that. So when you see the DEM goes above a certain height, you know those are not mangrove forests. So that's one of the measurements we use to distinguish the two types of forest. And the other one is to look at the spectral response of the different types of forests. It's also fairly difficult. They're both green, but that's how it's done.
So we talked about mangrove vulnerability to salinity, human activity, and coastal erosion. And this leads into the work you're doing with the Delta X project because you're studying deltas, which is where we find a lot of mangrove ecosystems. Now, I read that deltas globally are sinking. Is this correct?
Yes, so most of the large deltas currently are sinking. If you look in some regions of the world, they're actually moving cities around, even capitals, because they're literally sinking. In the Mississippi River Delta, we're seeing relative sea level rise, close to 10 millimeters per year. This provides a look into what will come in the future to other deltas in the world.
After the break, we learn more about the Delta X project and how Marc's study of the Mississippi River Delta is helping us understand ecosystem changes globally. So stay tuned.
Are you passionate about protecting our planet and tackling the challenges posed by climate change? Do you want to be a part of a remote sensing community that brings together the brightest minds in environmental science and engineering? Then you need to check out the Remote Sensing Environment Analysis and Climate Technologies Technical Committee, or REACT-TC for short. Here on the REACT Technical Committee, we believe strongly that interdisciplinary collaboration is key to making a real difference in our world. That's why we bring together experts from various fields to exchange ideas, share knowledge, and advance the science that drives our understanding of the planet. Whether you're a scientist, engineer, or simply someone who cares deeply about the environment, the REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society is a place for you. Together, we can make a difference, one discovery at a time. Visit grss-ieee.org and select the REACT Technical Committee to learn more.
Welcome back. Today we're speaking to Dr. Marc Simard, a senior scientist at the NASA Jet Propulsion Lab and principal investigator of the Delta X project, a 5-year NASA Earth Venture suborbital mission that examines how land is lost and gained in river deltas. Before the break, Marc mentioned that deltas around the world are sinking. He and his team on the Delta X project are looking at exactly what's causing this to happen so decision makers can better preserve and restore these fragile ecosystems. Let's jump back in. Now let's talk about your Delta X project. What is the Delta X project and what were you trying to understand?
Okay, the Delta X is a NASA Earth Venture suborbital program mission. We flew in 2021 3 aircraft nearly simultaneously. Each of these aircraft was carrying an instrument. With these instruments, we seek to calibrate and validate hydrodynamic and ecological models, which we can use to forecast the fate of different parts of the Mississippi River Delta. So we want to know if the delta will survive sea level rise. How do you do that? So we have to use models, but how good are those models? So we make sure they're good using that remote sensing data. So we used aircrafts rather than spaceborne data because of the tide. The tide comes in either once or twice a day. With a satellite, you cannot capture that. Only with airborne data can you do that. So with those aircraft, we actually went back and forth every 20 minutes and looked at the landscape and the water surface level. Two of these aircrafts were radars. So it is with those radars that we were able to follow that tidal wave. And then we had a third aircraft, we call it an imaging spectrometer. And it's a spectrometer because for every single pixel, you have 425 bands. So it's a full spectrum.
That's
And
a lot of bands.
that's a lot of bands, and you need very good memory on your computer to be able to process these data. So we've been doing a lot of analysis with these data sets. And the optical one, which is the imaging spectrometer called AVIRIS-NG, we had two purposes. One was to look at plant species distributions. So we were able to make a accurate map of plant species in two of the Mississippi River Delta basins. One is the Atchafalaya Basin, and the other one is the Terrebonne Basin. In addition to species, we also mapped water quality. In particular, what we wanted to know is how much sediment is found in that water. Because as sea level rises, there are two processes by which these wetlands can survive. The first one is by delivery and deposition of those sediment onto the wetland platform. So you want to build soil. So basically you're dumping sand on top of the wetland so it can rise with sea level, right? So this is the first process. The second one is through plant organic contribution. So as plants grow, they capture carbon from the atmosphere and then they build roots. They grow roots under the ground, which you can imagine inflates the soil, which rises. And then you have these plants that die every year and they deposit organic material on top. So you have sediment deposition from the river and you have the plant contribution to the system. So we have to look at those two processes and how they work together to contribute to the resilience of the Mississippi River Delta. And it is with those aircrafts that we made sure that those models that we built make sense. So we use the data to calibrate the models. Now we're at the point that we're finishing the calibration of the models, and we'll make some predictions this year or next year about the fate of the different parts of the two basins.
I'm just curious, what made the Mississippi Delta the perfect river to study?
So it is the perfect river because it is imperfect. We chose two basins. One of them is the Atchafalaya Basin. It has two large river inputs that dump a lot of sediment in the region. One is the Atchafalaya River itself, which is a distributary of the Mississippi River. And we have the Wax Lake outlet, which bring a lot of sediments, which gets distributed along the floodplain and deposited into the wetlands. And that region is actually growing. On the other hand, the other basin called Terrebonne is not fed by rivers. It's been cut from river inputs, so it has no river sediments coming in. And it's losing land, a lot of land. The only way for that region to survive is through the plant contribution. And that part is actually salty. There's salt and brackish marshes. And the Atchafalaya River, they're actually freshwater. Although it's tidal, it's freshwater. So they're very different ecosystems. So the Mississippi River Delta offers this perfect experiment where you have one place growing and the other one sinking. In other deltas around the world, there's also an issue with sediment input from rivers. We tend to put a lot of dams on large rivers, which breaks the sediment input cycle, right? If you put a dam, well, the sediment may not go to the wetland anymore, which means it's not keeping up with sea level rise. So that compounded with the fact that we will build shrimp farms, we're not helping the system. So it's a critical region for socioeconomic values, but also for ecosystem services that the region provides. So it's urgent to look at it, but it also provided the perfect lab experiment.
So you said we're not helping the systems, but does your research help us understand how to mitigate delta erosion?
Yes, I like that you use the word help. We don't provide solutions. We just observe what's going on and make models. And then it's for people that live there to decide how to handle it. But we have the knowledge, we provide the knowledge that is necessary to understand what's important and what impact the redistribution of fresh water with its sediment has, and what the impact of the shrimp farms and oil infrastructure and beaches and hotels have on the system, right? So we're providing the knowledge. We're not providing the solution. But our hope really is that science will help managers and stakeholders decide on the best methods to preserve or restore systems, whether it's coastal ecosystems or whether it's inland wetlands. I think we have enough data and knowledge acquired from that data and the models that we use to support good decision making or informed decision making.
Well, that's good news. Now, the other hoped for outcome of the Delta X mission was the potential to take what you learn from the airborne technology and apply it to satellites. What progress has the project made on this front?
Thanks for bringing up this question. It's great. So we use airborne technology because it provides this fast repeat and a possibility to measure tidal propagation inland, everything. You cannot do that with satellites. But we launched in December a mission called SWOT, Surface Water and Ocean Topography, which will measure water surface elevation over the oceans, the rivers, lakes, reservoirs, including all these tidal regions everywhere on Earth. It's a crazy mission. It will give us a type of data set and measurement that we've never had before. And in next year, just early next year, I think it's January or February, we're launching another mission called NISAR. It's a NASA ISRO synthetic aperture radar. So it's a collaboration with India that will enable measurements of water level change within wetlands globally. And we're pushing the limits of that type of remote sensing. It's not one of its objectives, but we're pushing its limits. And all that data, by the way, will be free to everyone. Everyone has access to it. So we cannot capture tides with those missions, but we'll have a very long time series, at least three years, 5 years, however long the mission will stay in space. And because we have these long time series, we can do some mathematics and retrieve a lot of information regarding tides. We call it river and tide discharge. So basically, there's like how much water is brought by the tides and how much water is brought by the river. So we'll be able, with those spaceborne sensors, to get global measurements of all those hydrological processes with all the wetlands in the world. So it's going to be really an amazing set of data.
That's very exciting. And in your view, how will these missions help us make decisions with respect to climate change?
Yes, so one of the important thing is at NASA, we also have an applications program. So we're trying to make the connection between our technology and the people on the ground. And I think that's the next step, is to help and support decision making. So we'll have to talk with the stakeholders and the people on the ground to understand their needs, how they could use the data, what type of models they use, how they make their decisions. So we can provide a remote sensing product, let's call it a remote sensing product, that supports their needs. At NASA, we haven't had a radar remote sensing system looking at land for a while. And having these two complementary sensors, I think, is going to revolutionize not only science, but its applications because of the availability of that data.
Yes, having access to all that data is definitely going to be a game changer. While we wait for the results of these missions, I think we still have to take action to help protect and reestablish our wetlands, and in particular, mangroves. So in your view, what steps should we be taking?
So I think the establishment of national parks and preserves is definitely a good way to preserve the mangroves. But some people live from those mangroves. So having communities involved in the preservation of the mangroves is key to keep their socioeconomic services, not only for those communities, but also for people living more inland. That's already ongoing and happening in some of the countries. Maybe it should be accelerated in others. And I think that's what should be done ASAP.
Since we're talking about action, what's one concrete action you think listeners could tackle in their own lives, either as, students, researchers, or as citizens, to support mangrove and delta protection?
So I don't know if it might sound silly, but I'd say go to the nearest wetland near you. And you'll understand a little bit more and connect to the wetlands, whether it's a mangrove forest or a marsh or inland wetland. You will see how it thrives with life, how beautiful and peaceful it is for the mind. And by going and visiting those sites, you actually contribute to local economy of the people living there. And if you can, I'm sure they have local programs where you can even plant mangrove trees and participate in some restoration activities there. So go to a wetland, go kayak there, go take a walk, go see birds, go fishing. Just go and enjoy wetlands. And I think it will help preserve those wetlands because we'll love them even more.
Plus, they'll have fun, right?
Oh, yeah. Definitely.
Well, that's all for this episode of Down to Earth. Want to learn more about Dr. Marc Simard and his research?
Yes, on Twitter and Instagram, it's Marc Loves Earth.
I love that handle.
Not only wetlands, Earth, the whole thing.
Don't forget to rate and follow us on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Irina Hansek of ETH Zurich and the German Aerospace Center for her support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.